energy. You all want it. You've all got it. This is a different kind of energy though. So, there are two types of energy. You've got kinetic energy and potential energy. Kinetic energy is energy in motion. Right now, I have kinetic energy. I am in motion, okay? If something's moving faster, it has a higher kinetic energy. If it's moving slower, it has a lower kinetic energy. The other type of energy is potential energy. Anything that is sitting on a counter, anything that is kind of sitting still, it has potential energy. It's stored, but there's different levels of potential energy. So say that I put this paper towel roll, if I put it on top of the smart board up here, that's going to have more potential energy up at the top of the smart board than it would if it was sitting on my counter. Why? Because if I was to knock it off of the counter or the smart board, which one is it going to fall harder from? Up at the top of the smart board, it will fall harder than it would be if it fell here. And also, if I was to take my roll of paper towels and put it on the floor, that's going to have an even lower amount of potential energy because it really has nowhere to go. Okay, so potential energy is energy that is stored. And then you have it transferred either way. You can go from potential to kinetic, you can go from kinetic to potential. Now, specific heat. This one is an easy concept that a lot of people forget about. Specific heat is the amount of heat energy needed to raise a temperature or to cause it to be lowered. Okay, it's from, you're raising it a degree Celsius, it's how much energy you need for that to happen. So in other words, it's resistance, a material presence to heat up or cool off. Water has a high specific heat. I'm going to talk about it a lot with this. Water takes a long time for the heat to get, for it to warm up, but it also takes a long time for it to cool down. That's because the amount of heat energy needed to raise the temperature of water is very high. Okay, so water has a high specific heat. So the front page of your reference tables, you're going to have the specific heat chart. You should take out your reference tables right now, pause the video, get out your reference tables or check it out on the internet and look at the first page. You need to find specific heat. It looks like this. Find it in your reference tables. You can see here that you have a whole list of materials, and then you have the specific heat that it takes to heat it up. So, liquid water takes 4.18 joules per grams times degrees Celsius. So that is more than, say, if you were to go all the way down here to lead. Lead does not need a lot of energy to heat it up or cool it down. Okay, lead actually has a low melting point, so you could heat lead up over a fire probably and melt it and reform it into something else. Okay. Next, from liquid water, there's solid water. Solid water doesn't take as long to heat up, or it doesn't need as much energy to heat up to make it go into liquid water. Water vapor is a little different. Dry air, not as much specific heat. It doesn't take as much energy to warm it up and cool it down as much as water does. So think about that. In the springtime, if you ever have gone to a lake, a pool, any body of water in the spring, and you were to jump in, the water is always stinking cold. Why? Because the sun hasn't been out long enough, the air hasn't been warm enough, and it takes a long time for the water to heat up. Why? Because it needs a lot of heat energy in order for it to warm up. But, like, I wouldn't say now being in October, but say early September when it starts to get cool outside and your pool is still like 75, 76 degrees and it's still kind of cool to go swimming in when the air is actually cooler than the water, that's because it still takes a long time for that water to lose the heat energy as well. Why? Water has a high specific heat. Water has a high specific heat. Don't forget that. So which phase does water have the highest specific heat? When it's in liquid form. And its lowest is when it's a water vapor. It doesn't take as long when it's a water vapor. Or it doesn't take as much energy, I should say, not as long. Time and energy kind of go hand in hand with this. So what's the relationship between specific heat and the rate of energy gained? So the higher the specific heat, there's the more energy it takes for it to heat up or cool off. So which substance has the lowest specific heat? Lead does. What does this mean? It takes up, or it will heat up the fastest, and it will also cool down the fastest. So actually when you take lead and you were to put it near a fire or heat it up, when you take it away, it does not take very long for it to lose its heat as well. So what does specific heat really mean? That you need more energy to raise the temperature or to decrease the temperature of water than land. So that means when you looked at your reference table, that basalt and granite, all those rocks, had a lower specific heat than water. So that's why water usually will stay warmer longer than the rocks or the sand or anything on the beach. So latent heat is potential energy stored during a phase change. And you can see the latent heat from the properties of water. So the heat energy, there's heat energy gained during melting. So when ice melts, it's actually gaining 334 joules per gram. And this is energy. So now there's heat energy released during freezing. So when water is actually kind of starting to freeze, it's losing heat energy, and it's going to lose about 334 joules per gram. Then when you go from evaporation, you go from being a liquid to a solid, you need way more energy for that to happen. You actually need 2,260 joules per gram in order for water to go from a liquid to a water vapor, to evaporate. And then heat energy released during condensation, so going from that vapor to being condensed, it's going to lose the energy. It's going to release that energy back into the atmosphere, or back into the, back out. Now what's going on in this demonstration? What change of state is being shown for each demonstration? So what do you see here? The water is evaporating off the person's skin, so that is going to be evaporation. Going from a liquid to a gas. This is going from off of a heated, I think it's a thermal pool that's there. What do you see happening here? That you had water vapor that then is doing what to the metal? That is condensation. Water is condensing on the bar. So it's going from a gas to a liquid. A lot of you like to see this in the spring when you have an icicle that has water dripping off of it. Therefore it is, oh no, melting. The icicle is melting. So it's going from a solid to a liquid. This happens a lot of times around here when this time of year you have water that's on blades of grass because of dew, but then it freezes. So this is going to be freezing, going from a liquid to a solid. And then this one's kind of fun. When something goes from a solid to a gas or a gas to a solid, it's called sublimation. So dry ice does it. Dry ice usually will go from a solid to a gas very quickly. So again, make sure when you're going through melting, it's gaining energy. It's taking energy in. When it's freezing, it's releasing energy out. When water is evaporating or vaporizing through vaporization, it's going to gain heat energy. And then with condensation, it's going to release that energy back out. It's going to release that much out. Okay? So as you go through each one of these cooling things, it goes through the cooling curve. So when it's a solid, it has to gain enough energy in order for it to melt. In order to become vaporized, it hangs out as a liquid, and then it becomes vaporized, and then it can become a gas. So this is the phase change chart. And this is just one without the writing on it.